Okay, in this video, let's talk some more about how we could represent information, and specifically represent information to make it more reliable, or to detect or correct errors. So specifically, we'll talk about the concepts of parity, error correcting codes, and distance in this video. Parity is probably one of the most common error correcting codes that's in use. Many times, codes will attach an additional parity bit to detect one-bit errors. So that bit, the parity bit, is set so that the number of ones in the entire code word is either odd or even. So if I have odd parity, the number of ones is going to be odd, and even parity, the number of ones will be even. So say, for example, I wanted to represent an ASCII character, and say I had the ASCII character A, which the 7-bit ASCII code for the character A is 1, 1, 4 zeros, and then another 1. So if I count the number of ones, I already have an odd number. So for an odd parity system, I would simply add an extra bit for the parity bit and make it a 0 to ensure that there's an odd number of ones. If instead I had even parity, the parity bit would be a 1 in order to make the total number of ones in the code word even. So let's look at an example with even parity and see how we can use this to detect when we have an error. If I send the character A with that additional parity bit using even parity, so this example on the right, and I transmit this, what is received? Well, let's say an error occurs in the 5th bit. I get 111010001 with that error in the 5th bit. Well, now when I receive the code, because I know ahead of time that it's going to be even parity, I've designed the code, I've set the parity bit so that there's an even number of ones. When I receive this value, I'm going to count the number of ones and see actually I have 3, 4, 5, an odd number. So this tells me that there's an error. What if an error occurs in the 1st bit, that parity bit? So that 1st bit is flipped from a 1 to a 0. Again, I check the number of ones and I have 1, 2, 3, so I know that there's an error. Now I know that there's an error in these code words because the parity is incorrect, but can I tell which of those bits have the error? And in this case with a single parity bit, no, I can't. But there are other codes that we can use that would allow us to correct an error. And in fact, there are many different codes and an entire area based on the theory of error correcting codes. An important characteristic of a given code and its ability to detect and correct errors is something called the distance. Sometimes this is also called the Hamming distance. So the distance between code words is equal to the number of bit positions in which they differ. How many bits do I have to flip or toggle in order to change one word into another? This is also sometimes called the Hamming distance, named after a really important person who developed a lot of the theory behind error correcting codes, Richard Hamming. So as an example, the distance between these two words are 1, 2, 3, 4, 5. Now we also have the concept of a distance for a code. And the distance of a code is the minimum distance between any pair of code words within that code. So for example, an odd parity ASCII code has a distance equal to 2. The minimum distance between any two ASCII characters with an odd parity bit has a distance of 2. Now, a little bit of theory here on how distance, and this concept of distance is really important to determining how many bit errors a particular code can detect and correct. Let's say that I have a code and I'm going to list all of the possible code words out in a table. And let's say that I list out all the possible combinations of bits, like I do in a truth table, and then I'm going to highlight the actual combinations that correspond to code words, valid code words in my code. And any of the combinations that aren't part of my code, those are considered invalid. And so when I move one position in the table, I'm essentially changing flipping one bit. So in this case, the distance between these two code words is 2. So this would be a code of distance 2. Now, if I have a single bit error, this is going to transform a valid code word into an invalid combination, hence allowing me to detect. Now, the problem with correcting it then is, I know that it's invalid, but I don't know if it came from code word 3 or if it came from code word 2. So I can say for this code of distance 2 that I'm guaranteed to detect all 1-bit errors, but I'm not guaranteed to correct any bit errors. Of course, I can make a guess, but I'm not guaranteed that I'll be able to identify which of these was the correct code word. Note that a odd or even parity code is of this type of code. It has a distance of 2. Now let's say I had a code of distance 3. So let's actually do an example of a code of distance 4. So to change any two code words into another one, I have to move 1, 2, 3, 4 positions. Change 4 bits to change any two code words, any code word into another valid code word. And in between any two valid code words, I have 3 invalid bit combinations. So what this means then is that if I have a single bit error, 2-bit errors, or even 3-bit errors, I'm still going to be able to identify that that's an incorrect combination and detect an error. So I'm guaranteed up to 3-bit errors. Now what about correction? Well, if it's a single bit error, and so I change from code word 2 to this position, most likely, assuming it's a single bit error, it came from code word 2, so I can correct that and change it to code word 2. The same thing coming from code word 1 over here, most likely the error caused code word 1 to change into this invalid position. Now for 2-bit errors, again I'm stuck in the middle here, and I'm not sure if this was meant to be code word 2 or code word 1. But I can now say with this distance 4 code that I'm guaranteed to correct up to a single bit error, 1-bit error. Okay, now with this in mind, the theory of error correcting code says that an error correcting code of distance d is guaranteed to detect up to d-1 bit errors and is guaranteed to correct up to d-1 over 2, rounding down, or at the floor, bit errors. So for example, for a distance 4 code, as you saw above here, d-1 or 3 was the maximum number of bit errors that I could detect, and d-1 over 2 or 4 minus 1, 3 divided by 2 is 1.5, round down gives me 1 bit errors that I can correct.